This meeting is being recorded.
In this next section of Chapter 4, we're going to review what's called the IUPAC nomenclature. So this is the standard system of our systematic naming of compounds from the International Union of Pure and Applied Chemistry. So we call that IUPAC for short. So we're going to look at some rules or some steps that we can use to strategically walk through how to name compounds. So our list for nomenclature would be to name the parent, which is the longest carbon chain. We'll do that first. Then we'll look for substituents and name them. And we also have to give each substituent a location. So if you recall, this term substituent is just a general term for anything that has been substituted in the place of hydrogen. So that could be a methyl substituent, an ethyl substituent, a cyclopentane substituent. Any of these can be considered a substituent. So let's take a look here. So step 1, we're told we have to identify the longest carbon chain. So say we start here at this carbon. If we follow this path this way, 1, 2, 3, 4, 5, 6, we would have 6 carbons in that chain. Well, let's see if we could try a different path and possibly find a longer chain. So again, we could start at that carbon, go down this path here. Say I take a turn over here. 1, 2, 3, 4, 5, 6, 7. So now I'm up to 7 carbons. But I might find another path that is even longer. So in the same compound, we'll start in the same spot. 1, 2, 3, 4, 5. Now if I go this way, I would have 6, 7, 8. 9 carbons in my longest chain. And that is fine. These are all single bonds, so we have free bond rotation. And just because this molecule looks kind of wrapped up doesn't mean that we can't take this path to find our longest chain. So we've chose a parent with 9 carbon atoms, so that would be a nonane as our parent. Let's move to how we can determine if we have the correct parent chain. So if we would have taken a different pathway, we still would have found that this incorrect structure over here has 9 carbons in its longest chain. Or actually, hold on, let's see. For this one, we have 1, 2, 3, 4, 5, 6, 7. So both of these have 7 carbons, rather. It's a different molecule in the longest chain. But we can see the correct structure over here has 3 substituents versus the incorrect structure over here would only have 2 substituents if we did this path in red. So both are heptanes, but the one on the left would be the correct over here because another rule of this longest chain is that we have the most substituents on that longest chain. So we found our parent would be a heptane, and then we would have a methyl substituent, an ethyl substituent here, and then a propyl substituent down here, instead of what looks like down here on the lower right, an isopropyl substituent. So let's see this in action here. If we have a substituent, when we name the substituent, or I'm sorry, when we name our parent chain, we're going to name it based on these names over here. So when we have 1 carbon, that would be a methane, and the parent prefix would be meth. So you can see ethane, propane, butane when we get to 4 carbons, etc. So I would definitely know how to name at least the first 10 alkanes correctly. And you won't really need to know these higher nomenclatures down here, but you may see an 11 or 12 carbon in a bicyclic compound. So we'll review in the next video what bicyclics are. It's just 2 cyclic structures, 2 rings fused together. So knowing undecane and dodecane aren't the worst idea, but definitely know the first 10. So again, how do we determine if we have a parent chain or a substituent? So in these cases here, we have cyclic structures. So we have cyclopropane, So instead of being a linear three-carbon chain, we now have a ring with three carbons. Same thing here with butane, but with four carbons, cyclobutane. And then five carbons would be a cyclopentane. So the only difference here when we have our parent would be that we add cyclo in front of whatever the alkane name is. So let's see if we can figure out what the parent is in either of these compounds here. So say we just went down this path here, we would have 2, 4, 5 carbons in our longest chain. But say we took a different path, this right here, 1, 2, 3, 4, 5, 6. So we would have a hexane parent here and one substituent. Let's try the same with this next structure. So say I just go straight across. That would be 1, 2, 3, 4, 5, 6, 7 carbons in my red highlighted chain there. Let's try a slightly different path. So I have 1, 2, 3, 4, 5, 6, 7. Well, now I have this pathway with 7 carbons. So it looks like 7 will be my maximum, but I want the highest number of substituents. So I'm going to go back to this original trace here. So we have 1, 2, 3, 4, 5, 6, 7 carbons, and we have the highest number of substituents. So we have 2-methyl and 1, 2, 3, a propyl substituent down there. This third compound, the parent will be the cyclic compound. So we have 1, 2, 3, 4, 5, 6, 7 carbons. So this will be a cycloheptane. And there is a problem with my numbering because my substituents, there's no way they could be on the lowest number if I call that carbon 4. So I would call this my carbon 1 when I gave the location of these two substituents. So we'll look at why that is the case on a future slide. We want the lowest numbering overall. So now that we are proficient in how to determine our parent, let's look at how we identify and name substituents. So again, we see in yellow here, the longest chain is our parent chain, and we have 3 side groups, 3 side chains that we're going to name as our substituents. So we have one up here, we have one down here, and then we have another one over here. So just like the roots or the prefixes to a 1-carbon chain, instead of meth for methane, we now call a 1-carbon substituent a methyl group. So that ending, the prefix meth is used, and then we add a YL ending to each of these. So ethane, eth, that prefix turns into ethyl, and propyl, etc., until we have an 8-carbon chain substituent down here, an octyl substituent. So let's look at these. Let's break these down. So now just the substituents are highlighted. So we have a 1, 2-carbon chain up here. This will be an ethyl substituent. Down below, we now have a 1, 2, 3-carbon substituent. So that's a propyl. And then this one, this line just stopping there, that's a methyl substituent. So that's a 1-carbon. Side group. So again, the YL ending is used instead of ane now. So let's keep moving along. We are continuing with step 2 here. So how do we determine, is it the parent or is it a substituent? So cyclic structures can be either or, depending on who has the most amount of carbons. So in this case, our parent over here on the left is a 6-carbon cyclic structure, a 6-carbon ring. So that would be the parent, more carbon. So 6 versus our substituent only has 1, 2, 3. So we have a propyl substituent on our parent cyclohexane. Looking over here now, our substituent, our side chain here, is a cyclopropyl group, and that's on our parent 1, 2, 3, 4 carbons in length, the butane. And notice we gave a locant here. We'll introduce this shortly, but this is my carbon 1, and then 2, 3, 4. I also could have had, a cyclopropyl here on carbon 2. So that's why we have to differentiate and give a locant or a location for that, that substituent, the cyclopropyl group. So there's another terminology called branching versus our linear carbon chains here. So we have, this is our parent here, what I'm highlighting in red. And then we have this branched side chain or a complex side chain here. So we would, just like our finding of parents, right, we would name or number the longest carbon chain. In this case, it would be a butyl side chain, right, a butyl substituent. And then at the carbon 2, we have a side chain off of our butyl substituent. So we're going to call that side group and give it a locant of 2-methyl. So the parent, whatever that name is, will go after. So what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we would have an undecane here. So we would have a 2-methylbutyl undecane if we threw this all together. So say we have some branching substituents that have different orientations, different atoms that are the connection site, for example. So we have a propyl group here, that's 3 carbons in length. Over here we also have, without much thought, we would say it's a propyl group as well. It's a 3-carbon chain, but notice over here the propyl group is connected at the carbon 1. Whereas here we could say it's connected at the carbon 2 site. So to know whether or not you have a propyl or an isopropyl group, you can just remember these orientations, or you can break down that side chain as a 1-methyl ethyl substituent, right? So it's connected here. So we would call this an ethyl substituent, and then on that ethyl substituent, there's a methyl group. So that's another way to ensure that you're naming them properly as propyl versus isopropyl. Let's look at something similar with butyl side chains, branched butyl side chains or substituents. So our butyl over here is linear, so we have all 4 carbons in a row. Then we have here 1, 2, 3, 4 again, etc. 1, 2, 3, 4 carbons here, and even this orientation down here. So the butyl substituents can have 3 different variations shown here. And again, whether or not we name it a 1-methylpropyl, like the sec-butyl here. So on the second carbon, we have that connection. Here we have an isobutyl. So it's connected on the first carbon here, but we know that if we named it, it would be a 2-methylpropyl, right? So 1, 2, 3. Propyl is our longest chain and our side chain and our substituent, and then we have this methyl on the carbon 2 versus the methyl group on our propyl group on the sec-butyl. Last but not least, this structure here, you'll see stuff like this. Some students call it a chicken foot for fun, and help them remember that this chicken foot is a tert-butyl group. And that's what we see here. So it's a tertiary butyl. So if we were to name this, our longest chain would then be 2 carbons in length. And then on that 2-carbon ethyl group, we have on the carbon 1, 2 methyl groups. So we call this a 1,1 dimethyl ethyl. So if you're ever in doubt, if you have a sec-butyl, isobutyl, or tert-butyl, you can name the substituents as IUPAC rules go, and that will differentiate the 1-methylpropyl, 2-methylpropyl, or 1,1 dimethyl ethyl. So let's take a look at this aspect here. So the carbons in our parent chain will have to be numbered in order to give locants or locations of any of these substituents or side chains. So in this case here, we see a 5-carbon chain as our longest chain for both of these structures. So they're both pentane parents. And depending on if we have the structure on the left or the structure on the right, the methyl substituent, the methyl side chain, is on the carbon 2 over here or on the carbon 3 over here. So these are similar structures. They would be isomers, but to differentiate one from the other, we have to give that location of the methyl group. So when we are numbering our carbon chains, we always want the lowest number possible for our substituents. So over here would be the correct numbering system, where we would end up with a 2-methyl heptane, versus over here it would look like a 6-methyl heptane, and this would be incorrect because it's the same structure, just numbered incorrectly. It doesn't have the lowest numbering possible. So the same thing applies if we have multiple substituents on our parent chain. So in this case, we have 1, 2, 3 methyl groups. Over here, 1, 2, 3 methyl groups. And if we number from left to right, we'll see that that gives us a 2,5,5 trimethyl heptane, versus on our right-hand side here, that will give us a 3,3,6 trimethyl heptane. So again, we look for the overall lowest numbering. So 2 is less than 3, and 5 is less than 6. So this is why the image on the left is our winner, is the correct structure. So one more time, right? Why is this correct? We go to each number, and as soon as we see a lower number beating a higher number, we would know that we have our correct structure. So always the lowest numbering system for our substituents. And the last guideline is if there is no other way to break a tie or to know, based on our numbering system, which substituent would have a lower number, then we alphabetize. So in this case, we have substituents here listed as a chloro. Bromine will be listed as a bromo group. And if we were to alphabetize this, bromine comes first, chlorine would come second. So we would call that actually a 5-chloro, and the 1-bromo would be correct. So this structure here, due to alphabetizing our substituents, is the correct structure. So we'll look at cycloalkanes next video, and also bicyclic compounds where we combine 2 rings together.